So basically, the name is helpful. What about the sequence just guarantees that the series will diverge? That's what we're saying. What about the sequence just will automatically guarantee that the series will diverge? No, game over. No more to say. No, not quite. I know Jacob knows. Yes, sir. Okay, but even more than that. As long as the sequence doesn't do what? Anything but what? Go to 0. So if the sequence converges to a finite value or diverges, yeah, so the only way a series could possibly converge is if the sequence goes to 0. The divergence test says anything else, the series diverges. If the sequence goes to a non-zero number, then you end up adding that same number over and over again once n gets big. And that's just that sum will diverge. Similarly, of course, if the sequence diverges, the series can't possibly converge. Okay? Geometric series. So here's that one. We've got the form AR to the n minus 1. Okay, remember? Geometric series is when your index, your n, is in the exponent. You keep multiplying by one more r to get to the next term. Those converge when the geometric sequence converges, right? We talk about geometric sequences converge between -1 and 1. And we know that for this one, we actually know the sum. A over 1 minus r. P series, 1 over n to the p. Converges for p greater than 1. 1 over n to the p. Okay, comparison test. Could be for divergence or convergence. So the sum an is divergent if this is in the most condensed form possible. If it's bigger than a known divergent series, right? If every term of an is bigger than the terms of one you know diverges, then yours diverges. Similarly, yours is convergent if it's smaller than a known convergence series. If every term is smaller than one you know converges, then yours converges. Okay, alternating series test. So now, with alternating series, if you have an alternating series, the non-alternating part, all that has to do is get to 0, decrease to 0. And then that thing will... So if you have an alternating series, you just look at this. And if you can conclude that sequence goes to 0, boom, it converges, right? Because the alternating effect really helps. Every other term is negative, positive. And we saw there's this honing in on the value. Okay? And then the ratio test, which we'll spend most of the time on today. Is it there? No, it's not even there. Okay, so we will definitely be looking at that closely. So I want to talk about, I want to do a couple of examples here. Let's look at this example. Where can I put it? I'll put it up here. I'll put it in blue so you can see it. All right, so what about this? Let's analyze this. So the first thing we might do is we might look at just the sequence. Does the sequence go to 0? Yes. Okay, we've got an actual problem to talk about then. If that sequence doesn't go to 0, or if we see that it goes to a non-zero value, series is divergent. But our series sequence goes to 0, so now we have something to actually talk about and think about. So what do we think? Is it of the form of one of these here? Okay, so is it a p-series? Literally, is it a p-series? No, a p-series is 1 over n to the p. That's it, 1 over n to a number. That's a p-series. But it sure looks a whole lot like a p-series, right? So what can we do? We got 1 over n squared plus n plus pi. So how about just, what do you think? Do you think this is convergent or divergent? Okay, why convergent? Okay, so if the sequence goes to 0, then the series converges. Is that right? Not enough, right? Not enough. What is it about this sequence, though, that we could say that it does converge? Yeah.
Well, we can kind of use the p-series.
Okay, good.
We can see that we have n squared,
Okay.
which is a p-value greater than 1.
Okay.
And just that alone, without subtracting anything else on the bottom, that alone.
Okay, so we know that 1 over n squared is a p-series that converges, right? P is greater than 1. So what about this plus n plus pi? Yeah, each term is going to be smaller than the p-series 1 over n squared, right? So we can compare this to a p-series that we know, right? 1 over n squared plus n plus pi. All those terms, and if we were writing this out, if I had room, we'd write this out. All the terms are less than the terms of the p-series 1 over n squared. And since the p squared 1 over n squared converges, therefore by direct comparison, this one also converges. Does it make sense? So we've got something, all the terms of this series we know are less than all the terms of a convergent p-series. So that's got to be convergent also. Is it okay? All right, what about this? Put that black circle around it. This is something that will happen a lot. So we saw that last one, we could directly compare it to a p-series. What about this? 1 over n squared minus n minus pi. So is that bigger, or all the terms bigger or smaller than 1 over n squared? All the terms of 1 over n squared minus n minus pi. Bigger or smaller than 1 over n squared? Now they're bigger because our denominator is smaller. So, conclusion? Divergent? Okay, so we can't, so who knows, right? So we've got a sequence, a series, all the terms are greater than 1 that we know is convergent, so it's the jury's out, okay? There are, it could be convergent or it could be divergent. So in this case, we still hone in on the fact that this is what? 1 over n squared. 1 over n squared, because what happens when n gets big? So now we're going to think about as n gets big, what is that sequence going to eventually become like? Okay, so before yes, the sequence goes to 0, but because as n goes to infinity, that is equivalent to really what for large n? 1 over n squared, right? Because for really big n, say 100 trillion, this number is 100 trillion times greater than that one because you multiply by n twice instead of just once. So when you get to really large n, these kind of just disappear. So this thing goes to 1 over n squared. So as n approaches infinity, this thing becomes like a whole lot like 1 over n squared for large n. Conclusion? Convergent, right? So even though we're not using direct comparison, we can look at the limit of the sequence. If we have an equivalent sequence that it's the same in the limit, we can say it essentially will do the same thing as that one. So even though all these terms are greater than the p-series with p equals 2, still in the end, it's basically essentially like 1 over n squared. Looking at the limit of that sequence. And so then the series will converge. It'll converge to a bigger number than 1 over n squared, but it will converge. So that's the reasoning you're going to have to use. The first example was direct comparison. I mean, it was like open and shut case. This one, we have to kind of think about it a little bit. If we look at it for large n, it still is like 1 over n squared. So it's not direct comparison. It's kind of indirect comparison or limit comparison, like limit comparison. Okay? You'll have to use that type of reasoning. Okay. Questions? All right, and so the ratio test was this. We brought this up last time. The ratio test is kind of that same kind of limit reasoning. So let's figure out what's going on with the ratio test. That if L is less than 1, we can say absolutely convergent. If L is greater than 1, divergent. And if L equals 1, no conclusion. So here's our first clue as to what this is kind of like. We've got a limit less than 1 or a limit greater than 1, giving us convergence or divergence. That should ring a bell, kind of. What is that like? No. Yeah, but the limit. So all right. So let's take a look. No, because P is an exponent, right? This is the limit of a sequence, right? So it's not really like P series. Because P, you're looking at the exponent. All right, so let's take a look at what this is about. What's that first series there? Geometric. And we said in a geometric series, what's the deal with a geometric series as you move from term to term? You just multiply the last one by r, right? And as long as that r is between -1 and 1, then those terms will get small enough, fast enough for that series to converge when you add them all up, right? Okay, so now let's just look at, this is now any series, right? So this is, I'm just writing any series here. It doesn't matter what it is. Not necessarily geometric, okay? I want to use that kind of same reasoning. How could we, if we go to get from A1 to A2, we don't know anything else about this. What could you say, what do you multiply A1 by to get A2? No. So what do you multiply A1 by? A1x equals A2. Solve for x, right? What do you multiply A1 by to get A2? A2 over A1, right? Solve for x. So times A2 over A1. And then what do you multiply A2 by to get A3? A3 over A2, etc. What do you multiply AN by to get the next term? AN plus 1 over, so that's generic then. For any series, what you multiply the current term by to get the next term would be AN plus 1 over AN, right? So with a geometric series, these all stay constant. This multiplier is always the same number, r, okay? But in any other series, that is not necessarily true. This could change. But as n gets large, what? If AN plus 1 over AN approaches, say it approaches 3/8. What if as we got large, that multiplier, it itself, that multiplier had a limit, and it got closer and closer and essentially became like 3/8? What would you say? Would you say this series diverges or converges? Because it's just like a geometric series with r equals to 3/8. So the ratio test is really asking the question, is the series becoming like a geometric series? Is the multiplier itself converging on a particular value? And if that value is between -1 and 1, if the absolute value is less than 1, then in the end, it's like a geometric series with that multiplier. So that's all the ratio test is. It's saying, okay, it's not a geometric series, but is it becoming like one? Is the multiplier that you have, is that converging in on a particular value between -1 and 1? And if it is, then it's like a geometric series, it's going to converge. If it's not, if it's greater than 1, if that's going to get converge on a number greater than 1, that multiplier, then it's like having r greater than 1, and it's going to diverge. Okay, if it converges on 1, then that's an indeterminate case. In some cases, that could be convergent. In some cases, that could be divergent. if, and I didn't finish. So then, okay, then it converges, like a geometric series that had an R of 3/8. Okay, so looking back at that one more time. So really, this an plus 1 over an is kind of like thinking about the multiplier, like R. Is it honing in on a particular value? Is this series becoming geometric? Is the series becoming a geometric series in the long run? And then we analyze it like a geometric series. If the absolute value is less than 1, convergent. If the absolute value is greater than 1, divergent. L equals 1, no conclusion. So let's do some more examples of this. We did one last time. We did this one. Okay? So oftentimes, these are come in fraction form. So rather than start with, so we're going to look at the limit as n goes to infinity of an plus 1 over an. So rather than start there, a fraction of fractions, we'll oftentimes just start with this instead. Do an plus 1 times the reciprocal of an. Flip what's given, and just start with that step, because that'll save a lot of writing, and a fraction of fractions often is hard to, it's kind of messy, okay? So we can just start with this step. Now before we get going here, let's take a look at this. Would there be another test that we might be able to use on this one other than the ratio test? So we're going to use the ratio test, but maybe we can predict beforehand what the result is. Is there another test that we could use? So, divergence test. Does the sequence go to 0? Yes. Okay, we've got a game here, right? We've got a match. Okay. What else? Is it geometric? No. Is it a p-series? No. What else we got? Is it an alternating series? Okay. So let's analyze it by the alternating series test. 7n squared over n cubed plus 4. If the alternating series test says if that thing goes to 0, boom, it's convergent. Game over. Does it? Right, yeah. So if we go back to our knowledge of sequences, the degree of the denominator is greater than the degree of the numerator. That thing goes to 0. Doesn't matter how fast it goes to 0, right? If it's alternating, doesn't matter how fast. So we could right away say by the alternating series test, this is convergent. But then we want to practice the ratio test. So the ratio test should tell us the same thing. We should get that it's convergent. So let's do it. Now the question is it absolutely convergent, right? So is that absolutely convergent or only conditionally convergent? Now let's find out. So an plus 1 is going to be negative 1 to the n plus 1. 7n plus 1 squared over n plus 1 cubed plus 4 times. And now so we're just going to take this as it is and just flip it over, right? Multiply by the reciprocal. N cubed plus 4. Negative 1 to the n. 7n squared. And so then the next step is kind of gather the like things together, right? So we've got the negative 1s, the n plus 1, and n. Gather those together. N cubed plus 4, n plus 1 cubed over 4, and this thing. So we're going to gather all those things together. So when we gather negative 1 to the n plus 1 over negative 1 to the n, what does that give us? Right? Remember how you imagine this? N plus 1 negative 1s multiplied together. And then n negative 1s multiplied together. So there's one more negative 1 on the top. But with the absolute value, it just kind of goes away anyway. Okay, and then 7. We're going to gather that together. And then that. Okay, so now we just have to know our sequences, right? So now we're evaluating the sequence of this thing. So this can just go because it's absolute value. So what is the limit of 7 times quantity n plus 1 squared over 7n squared? The limit as n gets big of that. Yeah, because what's our leading term here? Leading term is 7n squared over 7n squared. 1, right? So we're going to have 1 times 1. What's this? Leading term n cubed, also leading term n cubed? 1. So what does the ratio test tell us? No conclusion. Doesn't tell us. It gives us no conclusion. So if we had tried the ratio test first, then we need to go do something else. Well, we already did that something else, right? We already looked at the alternating series test. And by the alternating series test, we said this thing is convergent, right? Right? The positive part, the non-alternating part, decreases to 0. Now, is it conditionally convergent or absolutely convergent? Well, if it were absolutely convergent, that means if we took this off, if we took off the alternating, remember absolute convergence means take off the alternating effect and it would still converge. 7n squared over n cubed plus 4. Without the alternating effect. Convergent or divergent? So let's look at what the sequence does in the limit. What does that sequence do in its limit? I'm calling that thing Bn. Just like, what does it do? Bn goes to what? It goes to 0, but that we need to, before we actually evaluate the limit, what equivalent sequence is it really in the end? Okay, 7n squared over n cubed is going to be like, in the end, 7 over n. You see that? And yes, that goes to 0, but that going to 0 doesn't help us, right? We're trying to figure out what this thing is going to be like in the end. So as n goes to infinity, the non-alternating part goes to 7 over n. So conditionally convergent or absolutely convergent? It's not on your smartphone. Conditionally convergent or absolutely convergent? What does this do? Converge or diverge? That's the divergent harmonic series, 7 times, right? 7 times the harmonic series, which is divergent. Therefore, conditionally convergent by the alternating series test. So we got it was convergent by the alternating series test, but then we look at that, the rest of the non-alternating part, and say that's going to be like harmonic in the end. That's divergent. This thing needs the alternating effect to converge. So it's conditionally convergent. Okay, lots going on there. Ask a question if I lost you. Okay, try another one. You try it. Go, you try it.
I always wonder what the exclamation point about.
Right.
Like, is an N just really exciting?
Right. Okay, so all this should have been pretty easy. Writing down a of n plus 1, flipping a of n, and then gathering up the things that are like. That should have been okay. So this is kind of where it comes in. So how are we going to deal with n factorial over n plus 1 factorial? Well, if you're confident of what those mean, it's not hard, right? So how do we simplify or make sense of n factorial over n plus 1 factorial? So negative 1 is going to go in the end, so we can just take it out. But n factorial over n plus 1 factorial. Yeah, Gabe? Right. Right, so n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. But what's that? So without that first term, what is that? N factorial. So in fact, every factorial has as a factor all the lower factorials, right? So n factorial is always a factor of n plus 1 factorial. 4 factorial, 8 factorial, 7 factorial is always a factor of n plus 1 factorial as long as n plus 1 is greater than those values. Okay? So then, what does that become? If this is n plus 1 times n factorial, then n factorial and n factorial simplify to 1. So we're left with 1 over n plus 1 times, that should be easy by now. What? N plus 1 2's multiplied together. Imagine it. N 2's multiplied together. So 1 more 2 in the top than in the bottom. Limit is? How about the limit? So now the limit as n goes to infinity? 0, right? That's easy. Easy sequence, right? Easy sequence. 2 over n plus 1 goes to 0. Less than 1. Conclusion? Absolutely convergent. Meaning what? What does absolutely convergent mean? It means it doesn't need that alternator to help it converge. Take away the alternating effect, it still converges. Make all the terms positive. 2 to the n over n factorial is still going to get to 0 fast enough to converge. It doesn't need the alternating effect to help it. Make sense? Questions on this one? So could we have used the alternating series test on this one? Maybe, but we'd have to analyze the sequence. If we could show that that sequence goes to 0, then we can conclude it's convergent, but we still wouldn't know if it's absolutely convergent. So that's, in this case, that's where the ratio test is advantageous, because we get the best case possible. We don't have to go any further. We know it's absolutely convergent. Okay, another one. Go. Okay, so the homework due Monday, you have lots of complicated ones like this and the ones we're about to do. Gotta know how to do it. Here's what you got to watch out for. Is that right? It would be right if I added what? Yeah, it's that, right? N increases by 1. It's 3 times n, so 3 times the quantity n plus 1, which ends up being 3n plus 3. 3n plus 3. Factorial is? Thank you. Okay, and the top is? What factorial do we have now? N plus 2, right? N plus 1 plus 1. Like you just add those, n plus 2. Okay, now we're going to gather the like things together, right? Gather the like things together, and then you just have to know your factorials and exponents. So, yeah, this. Gather those together. Gather those together. And then the next step is where we see students have lots of trouble. So you just have to really know what exponents mean. So I've got 5 to the 3n over 5 to the 3n plus 3. What does an exponent mean? It means the number of times that you're going to multiply 5 together, right? I'm going to multiply 5 together some number of times. Now, how many times am I going to multiply it together in the denominator? 5. 3 more times, right? So this is some number of 5s multiplied together. This is that same number of 5 multiplied together with 3 more 5s multiplied on. So that will be, in the end, that will be 1 over 5 cubed. 3 more 5s, string of 5s multiplied together. 3 more of them in the denominator. So you're going to be left with that. All right, what about n plus 2 factorial over n plus 1 factorial? Well, in n plus 2 factorial, we have n plus 1 factorial, right? N plus 2 factorial is n plus 2 times n plus 1 factorial, leaving us with n plus 2. Okay, since we have the sorry, didn't finish here. Okay, limit equals n plus 2 over 125. Limit of that sequence? We all know that, right? Greater than 1. Conclusion? Divergent. Okay? Time to look at one more. We'll do it together. I'll do it as fast as I can. Okay, negative 1 to the n plus 1 over negative 1 to the n in the absolute value is just going to go away, so this time I won't write it. But if that's not a negative 1, if it's negative 2 or 3, then you want to have it because it's going to make a difference, okay? But with negative 1 to the n, inside the absolute value won't make a difference. So we have 4 n plus 1 minus 2 cubed, 6 to the n plus 2 over 3 times 2 n plus 1. That's a of n plus 1 without the negative 1 to the n plus 1 term. Flip it, a n flipped. So let's just go ahead and evaluate the limit here, or simplify without gathering together. We can see it, which gathers together. What's going to be the limit as n goes to infinity of? Okay, how about 6 to the n plus 2 over 6 to the n plus 1? One more 6 in the top than the bottom, right? Multiply together, so we're going to have a 6. Okay, 3 to the 2n over 3 to the quantity 2n plus 1. How many more 3's do we have in the denominator? 2 more 3's. This is 2n plus 2. There's 2 more 3's, so it's going to be 1 over 9. What's the leading term of this whole thing? So this is a polynomial. This is a polynomial. All we need is the leading term. Leading term is 4n quantity cubed. And what's the leading term of this? 4n quantity cubed. So we're going to have this polynomial with 4n cubed plus yada 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 and 4n cubed plus yada yada yada. What's the limit of that? Right, but the whole limit is 6/9. Conclusion? Absolutely convergent. Because the limit of that sequence is less than 1. That sequence is becoming like a geometric sequence with an r of 2/3, right? When n gets big, you basically have an r of 2/3, so it's convergent. Okay, web work due Monday.